Okay, so in section 3.1, number 5, we're given a function, f of x equals the quantity of x plus 2 to a 2/3. And they give you a picture along with this, but we don't have that picture in this. So what we'll do is we'll use a graphing calculator to get that image of what this looks like. They say to let's see, find the value of the derivative if it exists at the indicated extremum. And in the picture they give you x equals to -2. And if we throw -2 into this, we get -2 plus 2, which is 0. And 0 to any power except for 0 itself will be 0. So we know that the value of this function at x equal to -2 is 0. So let's try plotting it. So we have x plus 2 raised to a power of 2/3. Enter. But this doesn't look like what it looks like in the book, and that's an issue. All right. In the book, they have a picture where it is symmetric about this line of x equal to -2. So there's this other half that's not being shown here. And the reason for that is that when we have certain rational exponents, graphing calculators will take a shortcut method of using a logarithm to find out what this will evaluate out to be. And I have a little note on this, right? So if I have the quantity of x plus 2 to a 2/3 is equal to some function, then if I take a log of both sides, I can bring down that 2/3, right? And I'll have a value that I can put into this, right? I'll know what x is. So for example, x is positive 4, right? So I'll find the log of 6. And a lot of graphing calculators utilize logs of tables, and there's different methods that can easily calculate a value for log. But the problem with that is that if x plus 2 is less than 0, that's outside the domain of the logarithm function. You can't take a log of a negative number. So that's why some of these rational exponents, you get a hiccup. So the way around that is that certain functions, if you rewrite them in another way, you can change the order so that of what gets executed in order that we pass positive values into this logarithm function. And the way that we do that is we'll say x plus 2, and we'll square it first. All right? So then what you get out of this is always going to be a positive value. And then if I take that and raise it to a rational exponent, and this graphing calculator will try to use logarithms, and it has its own special method for figuring out what certain logarithms are. And if I hit enter on that, it does not understand. I put it in incorrectly. Let's see. We said x, quantity of x plus 2 squared. And that will be raised to a 1/3. There we go. And here it'll plot both the part which is greater than here and the plot which is less than here, and that is due to the fact that first I squared, giving myself a positive value, and then I took a rational root, and it used a logarithm to find that rational root. Some of your TI calculators will also use a very similar technique, right? So this is the picture, and they ask you to find what the value of the derivative is at this location. And we know from class that finding a derivative is a limiting process. So I have this picture where it comes down to there, and then it comes back up again. And if I want to find out what the value of the derivative is right there. That means put a tangent line through this that very closely resembles the rate of change of this function at this point. And the way that you do that with a limiting process is that you make a bunch of secant lines, and secant lines are made by choosing 2 points and drawing a line through them, right? And then we allow this point to get closer and closer to the original point until you find a limit. So for example, if I chose a point that's very close to that one, then the 2 secant lines maybe diverge just a little bit from one another, but they're very, very close. And then as you keep getting closer and closer and closer to this value, then what does that look like? But the problem with that is that if I can do that on the left side, it has to agree with what it looks like on the right side. So if I choose a point over here to be my other point and let this point follow the function down to the other, right, I get 2 different pictures for what the derivative might look like, right? I get a tangent line approximation that could be either this or it could be this. And you're not allowed to have an inconsistent answer, right? If I look at the algebra from this, if I take this derivative, I can use the general power rule here, and that will be that I bring down that 2/3, x plus 2, take the exponent and reduce it by 1, so 2/3 minus 1 is -1 over 3, and then multiply by the derivative of what's inside here, but the derivative of what's inside here by the chain rule is just 1, so that really doesn't matter. So I have 2, and then I can, since this is a negative exponent, bring it down into the denominator here, x plus 2 to 1/3, right? So at a value of at x equal to -2, I see that that isn't even defined in this derivative. There is no value of f prime at -2, because when I try to put that in to this, I get out 3 times -2 plus 2 to a 1/3, which equals 2 over 0 to 1/3 times 3, which is just going to be 2 over 0 to 1/3 is 0, so 0 times 3, well, that's just 0. So here I get division by 0, which that tells us that, this value of -2 is outside the domain of what I can put into this derivative. And what you would end up finding, though, is that if I tried to use the difference quotient, which is the definition of what a limit is, right? X plus delta x minus f of x divided by delta x. If I allow, and then the delta x is the distance from this point that I'm trying to find the derivative, I'll get one answer on one side and another answer on the other side, right? So as I let this point get closer and closer here on the one side, I get a different answer than on the other side. That is reflected in the algebra when you get things like the x value that you're trying to put into the derivative is outside the domain. That will indicate to you that the derivative does not exist at that one particular point. Graphically, that is shown by sharp changes in the rate of change. So if I have some function and it's going along happily and it looks very smooth, and then suddenly it takes a very jagged turn, this sharp point would indicate that the derivative does not exist at that point. So that is the answer to that. Okay, so that's number 5. Number 5 is that the value of the derivative does not exist. Right? It says find the derivative if it exists. Well, in this case, it does not.